This is our fourth lesson. Today we're going to develop a little better understanding of tangent lines and the derivative. In this lesson we want to explore how limits can be used to find the instantaneous rate of change of a function and the slope of the tangent line at some given x value. So first we'll look at average rate of change. So the average rate of change that you might recall is just the slope between 2 points, A and B, and that can be represented in many ways. On the interval from A to B, the average rate of change is the slope of the secant line that passes through the 2 points. It's the change in y divided by the change in x, and you can recognize that as the slope formula. The f of b minus the f of a divided by b minus a. Geometrically, that's the slope of this secant line, and here's a sketch of the visual representation for average rate of change. Now, a tangent line is different in calculus than what we know as a tangent line from geometry. A tangent line in simplest terms is that this is a line that best approximates the slope of the graph at any given single point. And you can see this looks like point slope formula. You're familiar with that from Algebra 2. y2 minus y1 is the slope times x2 minus x1. So point slope form can be used in calculus to find the slope of the tangent line. So the slope of the tangent line at C, that's the slope through only a single point that's touching the graph and the tangent line at that particular point. And if you can imagine this line going on, you know that tangent line would eventually cross that graph out here again, but it's tangent at the point that we're interested in, and we're calling that point point C. Also, okay, so I got that slide on there twice. So here we want to talk about the derivative. The derivative of a function f at x equals c is the slope of the tangent line at a single value, x equals c, and it's often called the instantaneous rate of change, or the derivative. And I have that graph here as well. So we can just add that to our graph. And that derivative is the slope of the tangent line, or the instantaneous rate of change. This piece right here in our formula, the limit formula, I'm going to point out this piece right here, this part of that expression is called the difference quotient. So if we take the limit of the difference quotient as the denominator goes to 0, we would be finding what's called the derivative, or the instantaneous rate of change. So average velocity, that was defined as the slope of the secant line, the change of y over the change of x, or using our slope formula, what we call the average velocity. Let's well, we've already seen geometrically what it looked like, but let's think about this. If I had some position function for the behavior of an object falling back to Earth due to gravity, if that position function was negative 4.9 t squared plus 12t, and I wanted to find the average velocity on the interval from 0 to 4, I could do that by finding the position at 4 and the position at 0, subtracting that, and then dividing by the length of the interval from 0 to 4. So using my calculator, the S of 4 is 17.6, and 17.6 divided by 4 tells me the average rate of change is 4.4 units per time. So I don't know what the units would be. Meters per minute or meters per second in this case. So we know that it's the slope of the secant line, or the average rate of change over the interval from 0 to 4. This particular example had no units given. In the last one, we can say the instantaneous velocity, that's our derivative. The derivative of the function is the velocity at a single instant in time. That's the slope of the tangent line. And if we take the limit of the difference quotient, we'll find out the derivative. So you can call that the slope of the tangent line, or the derivative of the function, or y prime, which represents derivative, or you can see that notation, the change in y with respect to the change in x. So that's the instantaneous rate of change, or the derivative. So we're going to want to use this equation to find our derivative, and we want the derivative. Let's say our function is the s of t is t squared, and we want the derivative at t equals 3. So we can find the derivative s prime of t by taking the limit as t goes to 3 of the f of t, well, in this case it's t squared, minus the f of 3, so if we substitute a 3 here, 3 squared is 9, over t minus 3. So factoring the numerator, we have the difference of two squares. So the limit as t approaches 3 of t plus 3 times t minus 3 divided by t minus 3. We can remove that common denominator and then take the limit at 3. So the derivative at 3 by direct substitution is 6. That tells us the instantaneous rate of change, or the derivative, is 6 units per time. So that could be miles per hour, meters per second, or feet per minute, or whatever the units are in your particular word problem. Now let's look back at defining a tangent line. So this is what I'm talking about from our past knowledge. In geometry, we know that a line is tangent to a circle if the line intersects the circle at only one point, and I'm giving that example here. But you can see this is a non-example. This is not true. But in non-circular graphs, that would intersect at one point, but that's not a tangent line. So on a circle, we can have a tangent line touching the circle in one spot. That's true for a circle, but not for some curvy graph. But over here in this example, you notice I'm tangent. This is my point of tangency. I'm tangent to the curve at that point, and I could call that point x equals c. And it touches the curve at that point, but you can also see it intersects, which is like this example. It is not tangent over here. So that is not a tangent point of tangency, but this is a point of tangency. So just so you understand that and not to get confused from geometry. So let's call this line 1 and this line 2. And we want to estimate the slope of the tangent line to the graphs at points A and points B. So if I think about point A, I could look at that point as -3, 0, and I could also use the point 0, 2 for point A. So the slope at point A is obviously a 0 slope. Two minus 2, so we got a 0 slope here. That tangent line has a slope of 0. But line 2, I've got this point here at point B, but I need another point And it appears to me that the point 3, 4, it looks like 3, 4 is also on line 2. So if we said for line B, we had the point 3, 4, and then I'm not sure what point B is, but if we come down here, it looks like 2, negative 2 is also on that curve. We don't know for sure, but it appears that that would work. Then the slope of the tangent line at point B could be 4 minus negative 2 divided by 3 minus 2. So that tangent line has a slope of 6 at point B. The derivative at point B appears to be 6, the slope of the tangent line. Example 3, we want to sketch the secant line through point P and point Q. So that would be this secant line right here. This is the secant line. And if you can imagine, I can't do this mechanically, I can't make it rotate, but if you can imagine that this line gets moved from this Q sub 1 up to this Q sub 2, that first slope through PQ is one rate of change. The second slope is another rate of change, but if I continue to move that slope around until it's only touching P, only touching point P, then that becomes my tangent line. You follow what I'm doing? I'm moving point Q closer and closer until point Q, which started out over here, the first point Q and the second point Q, and maybe a third point Q, until point Q and point P coincide on top of each other. Then the slope of the green line would be the slope of the tangent line, which is also called the instantaneous rate of change, or f prime of x, which is called the derivative, or the tangent line at point P. Okay, so we have this situation going on. Let me erase some of this. We have this situation here. So I've got this point and this point. So we have x, and we go over to the right. We have x plus a little bit more. I've added that distance, h, to there. So at this point, Q sub 1, my ordered pair is x plus h on the x value. And then over here, this y value would be the f of x plus h. So that's this ordered pair here, right? And this is going to be, this first line is going to be called the average rate of change, or the secant line. We could call it the secant line through point Q sub 1. And we're going to see how the difference quotient and the limit was created by this 3-part example. So let's say we are given 3x minus 4, and we want to find the f of x plus h. So I want to take the function 3x minus 4, and in place of my variable, I'm substituting x plus h. So my f of x plus h becomes 3x plus 3h minus 4. That's the f of x plus h. See how we're going to use it down here in the difference quotient. Then the f of x plus h minus the function. So my f of x plus h is 3x plus 3h minus 4. And then I'm going to subtract the function 3x minus 4 and simplify that. So we have 3x plus 3h minus 4 minus 3x plus 4. And when we collect like terms, everything without an h goes away. And we're left with the numerator of f of x plus h minus f of x becomes just simply 3h. And if I divide it by h and take the limit as h goes to 0, that can be taken away because that's 1. And now there's no h left to substitute, 0. So our rate of change, instantaneous rate of change, is 3. And this is the slope of the tangent line. But isn't this the slope of a line? So you can kind of verify the rate of change along any linear function is just the slope of the line itself. And in this case it's 3, and we proved it with calculus. Example 5. Example 4b is the same thing, just a little more complicated. If you want to give it a try for yourself, you can turn off the video and come back and join me and see if you have the same results as I do. In the first part, I ended up with x squared plus 2xh plus h squared plus x plus h. In the second part, you can see that we ended up with 2xh plus h squared plus h because the x squared and the x, after we subtracted, disappeared to 0. Then in the third part, if we take the difference quotient, set it up, factor out an h from each of the terms, then substitute 0 for that particular h that's left, we end up with 2x plus 1, which is called the slope of the function, or the derivative, at any point on the curve would be 2x plus 1. Then part C, it's just more of the same thing. So we're going to have 5x plus h minus x plus h squared, which gives us 5x plus 5h minus x squared minus 2xh minus h squared. And when we subtract the function, 5x plus 5h minus x squared minus 2xh minus h squared, and we're going to subtract 5x minus x squared. So that 5x would get rid of this 5x, and this would distribute to give us a plus here. So that would get rid of that, and our term would be 5h minus 2xh minus h squared for our difference quotient numerator. And we can use that. Let's see, let's take out an h from each of the terms and an h from the bottom, which would give us the limit as h approaches 0, with an h in the numerator would leave 5 minus 2x minus h, and then we're going to divide by h, so this common factor can be removed. And then if we substitute 0 for this h, that's going to be 0, and our derivative for h prime, our derivative for h prime is going to be 5 minus 2x for our function h of x. Was it h or was it f? Oh, it was f. I said h. I'm sorry, that's wrong. For f prime of x. And then our last example is with the square root, so that one is a little more complicated when we get to the bottom. X plus h is pretty straightforward. The difference between f of x plus h and f of x looks like that. But now when I set up the difference quotient, we'll have to rationalize our numerator, because we've got x plus h minus radical x over h. And we're going to multiply the numerator and the denominator by its conjugate, the quantity x plus h under the radical plus radical x, and do that same thing on the bottom. And you'll see as we distribute this, Our numerator is going to give us a nice term, x plus h minus x. So that's going to get rid of the x's. We're going to have only an h in the top after we distribute all the terms, and an h in the bottom, and then x plus h quantity plus radical x. So the h's are gone. There's a 1 in the numerator. We're going to substitute a 0 here, and our derivative is going to be 1 over radical x plus radical x. So our derivative looks like 1 divided by 2 square roots of x for our instantaneous rate of change. In example 5, we want to use those results from example 4 to find the derivatives for each function at a given point. So in 4a, our example, the derivative answer was f prime of x equals 3. So the derivative at 1 would be 3, since there's no x to substitute. In example B, our f prime of x was 2x plus 1. So our derivative at negative 3 is going to be negative 6 plus 1, or negative 5. In example C, our f prime of x was 5 minus 2x. So our derivative at 5 is 5 minus 10. So 5 minus 10 is negative 5. And f prime of x for letter D was 1 divided by 2 square roots of x. So the rate of change at x equals 4 is 1 divided by 2 times the square root of 4. So 1/4. And we're finding derivatives. Then 2 more examples to go. In the equation from 4b, x squared plus x, we said the point of tangency is negative 3, positive 6, and we got that right here. Negative 3 and positive 6. The slope of the tangent line at this point is negative 5. Is that right for 4b? Whoop, went the wrong way. Yes, negative 3. So we had the slope of negative 5. And you can tell this is negative 3 squared plus negative 3. So 9 minus 3 is 6. So when x is negative 3, y is 6. Just so you know where that came from. And then if we want to write the equation for the tangent line, we can use the y2 minus y1 is the derivative times x2 minus x1. And this is my x sub 1 and y sub 1. So y minus 6 is the derivative times x minus negative 3. And if we put all that together, negative 5x minus 15 plus 6, we would end up with slope-intercept form looking like that. Now, I don't know about your teacher, but I'm happy with this answer at this level. And then our last example is a practical application. We have a water balloon. It's thrown upward from the top of an 80-foot building, see, 80 feet building, with a velocity of 64 feet per second. The height in feet of the balloon can be bottled by this position equation, where t is in seconds from when the balloon was thrown. So we want to find the average velocity, or the average rate of change. That's going to be the s in the first 3 seconds. So the s of 3 minus the s of 0 divided by 3 minus 0. So our average velocity is 128 minus 80 divided by 3. I substituted 3 in here and substituted 0, which makes our average velocity 16 feet per second. So that's the slope of the secant line on the first 3 seconds, passing through 0 and 3. If we want the instantaneous rate of change, that's going to be the derivative, which is the velocity function. So to find that derivative, we want to take the limit as h approaches 0 of negative 16 t plus h squared plus 64 t plus h plus 80, and we're going to subtract negative 16 t squared plus 64 t plus 80 and divide that entire thing by h. So this becomes a little bit of a tedious nightmare. Multiplying and distributing that first statement is going to get rid of the 16t squareds and the 64t and the 80. Then simplifying that a little more, we got negative 32 th minus 16h squared plus 64h divided by h. And if we take out an h from this term and this term and this term and this term, we're left with substituting negative 32t minus 16 times 0, because we're letting h go to 0, plus 64. So we've found that the velocity is negative 32t plus 64 by using what was called the limit of the difference quotient. So our last part wants us to find what's the velocity of the balloon when it impacts the ground. So the question says, when is the position 0? Well, the function is negative 16t squared plus 64t plus 80. When is that 0? And if I divide by 16, I'm left with t squared minus 4t minus 5. And that can be factored as t plus 1 times t minus 5. And in real life terms, we don't have negative time, so we'll throw that one away. But now we know when time is 5 seconds, the balloon's going to hit the ground. And we also found the velocity, and we want the velocity at 5 seconds. So our velocity function was negative 32t plus 64. And that's going to turn out to be the velocity at 5, because we substituted 5 for time. And doing that arithmetic, we get 96 feet per second, and it's heading in a negative direction. So at 5 seconds, when the balloon hits the ground, it's hitting the ground at 96 feet per second in a negative direction, the negative. And that's our 4th lesson. We have one lesson to go in Unit 10.